I heard that. Okay. Before I was mucking around with microphone systems and stuff, and I just had this on a microphone that happened to be turned down completely. And that's why I couldn't hear anybody for 2 days. Took me that long to figure it out, so you know what you're up against here. Okay, so we got 1, 3, and XY written this way. We call this a row. We call this a column. And when we multiply a row by a column, very simple rule, we multiply the first number in the row by the first number in the column, and the second number in the row by the second number in the column. Okay, so we have 1x, and then we add them. Okay, 1x plus 3y. So 1, 3 times xy gives us x plus 3y, which is what we have here. Okay, then similarly, 3 negative 2 multiplied by xy gives us what? Now, to get you out of passive mode, I'm going to ask you to tell me what that is. I'm going to ask you to put that in chat. Give you just a couple of seconds to do that. If you don't want to embarrass yourself in front of everybody and not sure you have the right answer, you can do it privately, but there's no reason not to do it publicly. No embarrassment if you don't get it right. But please go ahead and enter that. Okay, I don't want to take any more time. Yep, there we go. And I think everybody's going to get it. So it's 3x minus 2y. So now this system of equations is equivalent to this matrix equation. Okay, by the rule I have here, it's should be very clear that it makes sense, at least, that when I've got 2 rows multiplied by this column, the product is going to be the first row times the column, which in this case is x plus 3y. And the second row of the result is the second row times the column, and that's going to be 3x minus 2y. And in linear algebra, almost everything we do is done with matrices, okay? But it represents systems of linear equations, okay? So matrices can represent linear equations. Now, this matrix really doesn't represent this linear equation, but here's a matrix equation. Well, here's the matrix equation that does, because then to say that when I multiply this by this gives me this, then this should equal this. So that the equation here expresses exactly what the simultaneous equations express. Okay, so so it's very easy translation. If you understand matrix multiplication, then you pretty much have it. Now I'm going to mention one thing. I'm not going to invert the matrix right now, but we can invert matrices. Just a preliminary thing to get the wheels turning here. 1, 3, 3 minus 2, inverse multiplied by xy. Oh boy. I didn't leave myself room to write this out, so I just went ahead and wrote the wrong thing over here. I have to write this in 2 lines. Okay. This multiplied by xy, if this equation is so, is equal to this, where the inverse of this matrix is the matrix you multiply by this one to get the identity matrix. Okay, so the inverse is defined by whatever matrix it is that multiplies this one and gives us this. And the identity matrix multiplied by xy, you can see 1, 0 times xy is just going to give you x. 0, 1 times xy is just going to give you y. So that xy equals this. I'm going to have to lift up this board a little bit because I suspect that when the video is done, this is going to be obliterated by a watermark. So there we have it. And what this tells you is that if we can invert this matrix and find the inverse of the matrix, then we just have a simple matrix times 5, 3 that gives us our solution. And that might seem like a lot of trouble to go to solve the system. And it is actually if you have 2 equations and 2 unknowns. But if you have like 10 equations and 10 unknowns, it's a big deal. It's much simpler. And we're going to see that. And we're going to see that before too long, actually. Okay, well, this is a little bit of a digression from where we're going here in this, trying to prepare you for this section. But there you have it. And it's kind of worth storing away. We'll see it in more detail quite soon. Okay. Now I'm going to do another thing with matrices that isn't involved with a matrix equation. It's involved with what we call an augmented matrix. Okay, the augmented matrix for this system is the 1, 3, 3, -2, same as matrix we have here. And then we maybe make a dotted line here and put the 5, 3 here. And this represents our system. It's kind of a shorthand way of representing this whole system. Okay, well, if I want to solve this system by elimination, then it should be clear that I can subtract 3 times the first equation from the second equation, and that'll eliminate the x term in the second equation. So I'm going to do that, but I'm going to do that with these rows of numbers. So I'm going to say I can replace this matrix with the matrix that consists of the first row of this matrix. And here, the second row minus 3 times the first. okay? Now, if I multiply the first row by -3, what do I get? Enter that for me. The first row times -3, -3 times the first row. Just want to make sure everybody stays oriented here. Okay. Okay. Thanks, but it's not 0 because I've got to multiply 3 by all 3 numbers here. Okay, -3 times the whole first row. I think what you're saying is that if I multiply the first row by -3 and add to this one, the number here is going to be 0. That's absolutely correct. Okay. Okay. Now you're a step ahead of me, but I think you're right. Yeah, you're right. Okay. Now that's a good answer. It's the next answer I'm asking for. What I'm asking everybody else to do here is if I multiply this first row by -3, what do I get? Well, -3 times 1 is -3. -3 times 3 is -9. Yeah, exactly what we just saw there. Thank you, Jacob. Okay, so there it is. And if I then add that -3, -9, -15, which you can see there in chat, to the 3, -2, 3, what am I going to get? Well, that's going to give me second row -3 times the first, and that's going to give me 0 here. And then we're going to have the -9 that we get here, and the -2 is going to give me -11. And the -15 that I get here added to 3 is going to give me -12. Okay. Now, this is totally equivalent to what I get if I multiply the first row here by -3 and add to the second row. And I'm going to get -3x, which added to 3x gives me 0. And I'm going to get -9y added to -2y is going to give me -11y. And that's represented here. And -15 added to 3 is going to give me -12. So that by operating on these rows, I'm doing the equivalent of operating on these equations. Okay, so we call these row operations. And clearly I can mimic anything I want to do with these equations by doing row operations on this matrix. Now, if I want to continue the solution, what would my next step be? Well, this represents the equation -11y equals -12. You know, that's what this row represents. And if I want to solve this equation, I'm going to divide both sides by -11. Well, in the matrix, my next step is, well, the first row is just going to repeat from up here. I'm not doing anything in this step with the first equation. My second row is just going to be I'll do it this way, -1/11 multiplied by the second row. And if I multiply this row by -1/11, clearly we're going to get 1 here, and we're going to get 12/11s here. Now, what does this stand for? What equation does this row stand for? Now, can you enter that for me? Very good. And I'm sure everybody else was thinking the same thing. So Yeah, it's y equals 12/11. Okay, it's very simple. Okay, now, if I'm doing these equations and I've got y equals negative 12 or equals 12/11, what am I going to do with that? I'm going to plug that back in here. Okay. That's equivalent to adding, well, actually, this one isn't exactly analogous to what we do. What I'm going to do is I'm going to add -3 times this row to this row. Okay. So I'm going to do -3 times the second row plus the first row. And what's that going to do? That's going to wipe out this 3 and give me a 0. And my equation is going to be 1x equals whatever I get here. So let's just do that. Okay, -3 times the second row is -3 36/11. Okay, so I've got 1, 0, and then I've got 5 plus 36/11, 0, 1, 12/11. And of course, I can simplify this to what, 55 and 36 is 91. Okay, so it'd be 91/11. And here I've got 0, 1, 12/11. Okay. Now again, I don't have room to write it here, so I'm going to write it here because I want this last step to be clear. Okay, what I've done here is if I have gotten my system down to this one, which is x plus 3y equals 5 and y equals 12/11. Okay, then I can take the second row and I messed up. This should be minus 36/11, shouldn't it? Which will make this 19, I think. Okay, we'll see. Okay, so I could have multiplied this equation by -3, and then I could have added that to this equation so that x plus 3y equals 5 and -3y equals -36/11 adds up to x equals 5 minus 36/11. So that this row operation, this idea of adding multiples of rows to other rows works just fine. This isn't quite the way you would generally write it out. You'd say y equals -36/11, so then you take this and plug it in here and so forth, and you know what that is. But using row operations, we can accomplish the same thing. Okay, so this idea of row operations is very profound, very important. This process is called Gaussian elimination. And this form is called row echelon form. Okay. Uh, so you can read the terminology, but this is the process. And you might wonder, why do we do it this way? Well, actually, this is simpler than this because you don't have to write out all the X's and the Y's. You just operate on the numbers and everything works out. Okay, well, that's basically Gaussian elimination. And so we're going to take that as an introduction. And Donovan, thanks. I didn't see your note there, but it's unusual that I actually caught my own error. And please continue to correct me if I do make errors, or just draw attention to errors. Okay. Well, there's that. Okay, so that's Gaussian elimination. I think you'll have very little trouble with it. Now I'm going to leave it to you to read the book on row echelon and reduced row echelon form. This is reduced row echelon form. What you have, you can look at this. This is called your main diagonal. Okay, what we see here. Switch the screen back so I can see what I'm doing. Okay, so here's your main diagonal, and you have numbers on your main diagonal and nothing below the main diagonal. Now there's a little more to it than that, but that's an echelon form, a reduced echelon form. A reduced and let me make sure I've got the book's terminology. Okay, yeah, that's row echelon form. And reduced row echelon form, you reduce everything to ones here. Okay, because having ones here tells you like X equals, Y equals, and so forth. Okay. I'm trying to sort out what's in section 1.2 and what's in section 2.1, because those will both be due before Tuesday. Let me also tell you that I'm going to do some videos for you for Tuesday because I'm going to have to take a day's leave for the first time in almost a decade. My wife has an appointment in Charlottesville, and I have to take her up there and back. She's had some medical treatments, and she's going to get an all clear. We got to go up there to make sure it's an all clear. So, and she's not allowed to drive until she gets that all clear. So I'll be driving her up. She'll be driving me back, but it's going to take all day. So I'm unfortunately going to have to miss Tuesday's class. I'll send out an email. So it's be a relaxing day. It's fairly relaxing drive up there. It's not too long. But I don't like having to miss a class this early in the term, but I apologize for that. Okay. So okay. I'm debating whether, just looking at the time and so forth. Yeah, I'm going to leave that for you to understand through the text. I might come back and talk about it. Okay. An important application of systems of simultaneous equations and matrices is curve fitting. Okay, so simple example. We got 2 points on the plane. And let's go ahead and give these points coordinates. Let's say this is 1, 3, and this is, okay, if this is 1, this is probably 4. If that's 3, this is probably 6. Now there's a straight line that fits these points. And we want to find that straight line. Of course, you've got the 2-point formula for straight lines and all that stuff. But we're going to do this with the matrix equation because what we do then can move to a greater number of points. And we can get a polynomial that goes through any set of points we want using matrix methods. So I'm going to demonstrate it with a straight line. So we assume our equation has the form ax plus by equals c. Then the first point implies the equation, well, x equals 1, y equals 3. So we have 1x plus 3y equals c. And we have this. And that's not the way I want to formulate it. I'm sorry. That introduces an extraneous variable. Hopefully I can write over this, we'll see. Okay, we're going to assume y equals mx plus b. So 0.13, y is equal to 3, 3 equals 1m plus b. 4, 6 implies 6 equals 4m plus b. And here's our system. We can write that system as 1, 1, 3, 4, 1, 6, where this row represents your M and this row represents your B. So it's 1M plus 1B equals 3, 4M plus 1B equals 6. We can reduce this system. And it goes very much like what we did just said. So we reduce the system. And we're going to get a 1, 0, 0, 1. And should close the parentheses. And I'm going to cheat a little bit. We're going to get 1 here. And we're going to get 2 here, I think. Okay. And the process of reducing, I'm not going to go through that, but the reduced matrix, oh, I wish I had done that. Okay, the reduced matrix is going to be here, which tells us that M equals 1, B equals 2. So the equation of the line is Y equals X plus 2. Okay, and I didn't intend it that way, but I'm glad it worked out that way because I could do it in my head. Okay, so Y equals X plus 2. That worked just fine. Okay, so that's pretty straightforward. You understand how to do the reduction, and by the time you get to a problem like this, you will have done a reduction. Okay. Now, if you have 3 points, let's say, oh, I don't care, let's see, 1, 10. And if that's 1, that's about 3. If that's 10, that's about 4. 3, 4. And here, if that's 3, that's probably 7, 2. Okay, so let's say we have these 3 points. A polynomial of degree n can fit exactly through n plus 1 points. Okay, straight lines of polynomial of degree 1, it'll fit 2 points. Polynomial of degree 2 will fit 3 points. Polynomial of degree 2 has general form y equals ax squared plus bx plus 3, the familiar form of a quadratic. Okay, so what do? We can write out 3 equations. We can write out an equation for every point. So for the first point, we get 1 equals 10 equals a times 1 squared plus b times 1 plus c. The second point, y is 4, x is 3, plug it in here. We get 4 equals a times 3 squared plus b times 3 plus c. And at this point, y is 2, x is 7. We get a times 7 squared plus b times 7 plus c. Then we do the arithmetic, and we get a plus b plus c equals 10. 9a plus 3b plus c equals 4. And 49a plus 7b plus c equals 2. Now that's 3 simultaneous equations. We can easily solve them. We could subtract 9 times the first equation from the second and eliminate a. We could subtract 49 times the first from the third and eliminate a. And then take the 2 equations we have left. That'll be 2 equations in b and c, 2 equations and 2 unknowns, and we can solve that. Okay, well, that's what you did for homework. But what we're going to do now is we're just going to say, well, I just write this as a matrix equation, 1, 1, 1, 10, 9, 3, 1, 4, 49, 7, 1, 2. And I can reduce this to 1, 0, 0. Now I'm not going to solve this one in my head. Okay. 0, 1, 0, 0, 0, 1. And then we're going to get some number here, some number here, some number here. So we get, this stands for A equals this number, B equals this number, C equals this number. So this is A, this is B, and this is C. So if we do the reduction, we're going to get our values of A, B, and C. And of course, we plug those into this equation and we get our second degree polynomial. If I've got 4 points, I can do the same thing. I'd have to have like an ax cubed plus a bx squared plus a cx plus a d. And I'd get a matrix with 4 rows and 4 columns. And I'd have a little more work to do. But you understand that it's not difficult, or at least you will understand after you've done a few of them. It's not difficult to reduce an augmented matrix like this. And having done that, you get your solution. And it's probably a lot easier to do the augmented matrix, the bigger the matrix is, than it is to write out these equations in every step and do all the operations that way. So it's one important application. Another application is to networks of circuits. And I'm going to have to leave that for you to read. I might well do a video on that. Leave myself a note here. We might have time to come back and get it. But there are a couple of things that we want to talk about regarding matrices. Now, I think you're going to find section 2.1 to be pretty straightforward. I haven't noticed that people have any real difficulty with it. But I want to talk about a couple of things that you probably do better to see before you start reading. So let's just take matrix 1, 3, 3, 5, and see what it means to multiply this matrix by itself. Okay. Now, before I do that, I'll just mention, if I want to add a matrix to another one, if I wanted to add this matrix to this matrix, I just add the 1 and the 1. That gives us 2, 3 and the 3 gives us 6, 3 and 3 gives us 6, 5 and 5 gives us 10. That would be the sum of the two matrices. If I want to multiply a matrix by a number, I multiply every number in the matrix by that number. Very simple. Multiplying the matrices, though, you might think, well, multiply 1 by 1, 3 by 3, 3 by 3, 5 by 5. It doesn't work. Okay, it doesn't make sense in a way that we'll maybe try to bring out, but just right now, take my word for it. In terms of everything that we do with matrices, that wouldn't make a bit of sense. It wouldn't be consistent. It wouldn't have an associative law or a commutative law or any of that. Of course, we don't have commutative law for multiplication of matrices. The matrices would not behave algebraically like we expect things to behave based on what we know about algebra of numbers. Now, the algebra of matrices is a little different than the algebra of real numbers, but not that much different. One thing you don't have is matrix multiplication isn't commutative. But other than that, it pretty much mimics what we can do. We don't have division, but we do have multiplication by the inverse. Now, that's a lot. You won't understand all of that until you work it out, but those are some of the reasons that we don't multiply matrices in the way that might seem obvious from the way we add them. Okay. Well, when you multiply rows, you multiply first number in a row by the first number. When you multiply a row by a column, okay, when you multiply matrices, you're doing rows times columns. Okay, so I'm going to write this out. I'm going to write it out as a big matrix. I'm going to say, okay, and you know what? I don't want this to be the same as this matrix. I'm going to make this 4. I'm going to make this 13. I'm going to make this 15. I'm going to make this -3. Okay, so now I got 1, 3, first row, first column. Okay. I can multiply the first row by the first column, first row by the second column, second row by the first column, second row by the second column. Okay, those are the ways I can multiply rows by columns. I'm going to do that in every possible way, and I'm going to put those products into the product matrix, and I'm just going to do it, and then I'm going to explain the rule. Okay, well, yeah, I'm going to explain the rule now. The first row times the first column goes into this matrix here in the first row and the first column of that matrix. First row times second column goes into the first row and the second column. Now remember, these are just going to be numbers. We can easily multiply these and get the numbers, and we're going to do that in the next step. Okay, so there's this number here and a number here. But the number that's going to go here is first row times first column. The number that goes here is first row times second column. Okay, then, of course, we're going to do the second row times the first column. And where do you think that's going to go? Second row times first column. Well, it's going to go in the second row of this matrix and in the first column. So we have 3, 5 multiplied by 4, 13. And then over here we have the second row times the second column. And I'm not going to write down here. I know what's going to happen. Well, yeah, I probably have room to get this in. It's going to be small. Well, first row times first column. 1 times 3 is 4. 1 times 4 is 4. 3 times 13 is 39. So I believe that's 43. 1 times negative 3 is negative 3. 3 times 15 is 45. And 45 and negative 3 gives us 42. Now, I'm not going to say all that here, but I'm going to get what? 12 and 65, which is 77. And I'm going to get negative 9 and 75, which is 66. Okay, that's the product of the matrices. Okay, now, what if I wanted to multiply this? Can I do that? Well, sure. As long as the length of my row is equal to the length of my column, I can multiply the row by the column. Now, I'll say if the length of the row is not the same as the length of the column, you can't do it. Okay, you got to have something in the column to match everything in the row, and everything in the row has to match something in the column. So we have what? I'm not going to write it out this way, but the first row times the first column is going to be, oh, what the heck, I'm going to write it out. 1, 3 times 1, 2. 1, 3. I'm not going to have enough room. I do that to myself all the time. And then we're going to have 1, 3 times 4, 1. And then it's going to close off the matrix, etc. Don't have room to write it out. It's going to overlap everything there. But that's what I'm doing. First row times first column, first row times second column, first row times third column, and so forth. And these numbers are easy. We can do this in our head. Now, my head often makes errors, so watch me. Don't believe my arithmetic. But we're going to have what? 1 and 6 is 7. And 1 and 9 is 10. And 4 and 3 is 7. And 3 and 10 is 13. And 3 and 15 is 18. And 12 and 5 is 17. Works out just fine. Okay. Now you see examples in your book, and your book is going to tell you you can't row, if the rows and columns don't have equal length, you can't do the multiplication. So like if I wanted to reverse this and multiply this row, this matrix by this matrix, it wouldn't work. Okay, so I take, what if I want to do 1, 1, 4, 2, 3, 1, multiplied by 1, 3, 3, 5 equals what? The rows don't match the columns. The rows of this one, the columns of this one, have different lengths. We can't do it. This is undefined. Okay. So that's matrix multiplication. Very simple. You'll get used to it rather quickly, and I don't think it's going to give you any trouble. Okay, now here's something that's going to be I mean, everything that we're talking about here is going to be a big deal in the course. Okay. If I have this matrix multiplied by xy, I'm not going to use xy here. I'm going to use x1, x2. And I'm going to use like x1s and x2s and so forth, instead of xy's and z's, because if I'm using xy's and z's, I eventually run out of letters. If I use subscripts, I'm never going to run out of numbers. If I want to do a matrix with 1 million columns, and those do exist, and we have to deal with them in data analysis, I'd better have 1 million subscripts, and there aren't enough letters, okay? But there's plenty of integers to use for the subscript. So we're generally going to use like x1 and x2 for the subscript. Okay. Okay, well, actually, that was really kind of ignorant. I'm writing columns of length 2, so I just kind of wrote a column of length 2 there. What was wrong with that? Want to tell me what's wrong with that? Well, you probably don't have time to write it out. I better have a column of length 3 here to match the rows of length 3, okay? Okay, so I guess I'll write it out. This is equal to this. Very straightforward, 1 times x1, 3 times x2, negative 1 times x3, and similar for the second column. This is equal to x1 times the column 1, 2, plus x2 times the column 3, 5, plus x3 times the column negative 1, 4. Now, I think I've left myself enough room down here that the watermark won't interfere, but just in case, okay, here we go. Right? Okay. Now, does that make sense? Well, let's make sure we understand that it makes sense. So this is equal to x1 times 1, 2 is x1, 2x2. Because when we multiply a number by a matrix, this is a matrix, okay? It's a matrix with just a single column, but it's got 2 rows. Okay, then x2 times 3, 5. And this should have been x1 here. And then equal to this. But now when I add these, I add numbers in the first row to the numbers to each other, and I add the numbers in the second row to each other. And now we see that this matches this, so the equality is justified throughout. Okay. Now this thing here is called x1 times 1, 2 plus x2 times 3, 5 plus x3 times negative 1, 4 This is called a linear combination of the columns. Got to continue up here. Columns 1, 2, 3, 5, and negative 1, 4. Here's the big deal. These columns I'll just say vectors in the XY plane for right now, because I'm not sure how much terminology that you're familiar with regarding vectors. Okay? That is, if I've got the plane XY, and I'm not going to call it XY, I'm going to call it X1, X2. So I say XY, but I'll also call it X1, X2 plane. Those are braces, not brackets. This is not a column vector. It's just two ways of referring to the plane. I'm doing it this way. Then the vector 1, 2 means you have a coordinate 1 here and a coordinate 2 here. And you got a point here and you got an arrow, and there's your vector. Now in your prerequisite courses, you should know about vectors. And hopefully you do. If not, you're going to have to learn some things. But it's fairly straightforward. Okay, now we got 3, 5. Well, 5 is up here a ways. And I'm going to maybe not do this to scale. But here's your vector 1, 2. Keep my notation straight. Here's my vector 3, 5. And my vector negative 1, 4. We go over here to negative 1 and up to 4. And it's going to be here. A linear combination of these vectors depends on what x1, x2, and x3 are. And there's little ambiguity in my notation because I've got x1 and x2 here. So instead of x1, x2, and x3, I'm going to call it C1, C2, and C3. Some constant number multiplied by this vector plus some other constant number times this vector plus some other constant number times this vector. Okay. For example, well, okay. Don't want to go into that detail because you don't need it right now, but this is extremely important idea and you're going to see it. A linear combination of these vectors corresponds to adding the vectors. So if I do just a linear combination of, if I add this vector to this vector to this vector, I don't have room to do that on this board, but I guess I can do it over here. So that, let's say we just do 1, 2, plus 3, 5, plus negative 1, 4. We can illustrate that because, okay, here's one, okay, here's our plane. Okay, I'm gonna draw like this. Give myself room. And hopefully you're familiar with vector addition. You add vectors head to tail. Tell me, just give me a yes or no. Are you familiar with the idea of vectors and vector addition? Could even be yes, no, or maybe. Standard topic in pre-calculus 2. Yes-ish, that's a maybe. Okay, maybe. Okay, well, we'll be sure to develop this a little bit because that's kind of the information I need. Anyhow, here's how you add the 3 vectors. Here's the 1, 2 vector. And now the 3, 5 vector. It's quite a bit longer, it goes off in this direction. Yeah, and you know, I'll probably saying that people have not necessarily been exposed to vectors. I'll probably do a couple of videos on it as soon as I have time to do it, and hopefully have time this weekend. Because you want to know this. I'll also double check your book to see how much detail they go into when they introduce it and try to supplement that a little. Okay, anyhow, we got negative 1, 4 here. It goes like this. So it's like we take this vector and put it here. We take this vector and put it here. We take this vector and put it here. Now, I'm not doing a great job of and if you haven't seen them, you're going to see a whole lot of them in your curriculum. Okay. What engineering course are you all taking right now? The curriculum has changed a little bit, and I actually should know. Anyhow, here's the sum of the 3 vectors, and the sum is then this. So this vector here would be this. And of course, that can be added. 1 and 3 and -1 is 3. 2 and 5 and 4 is 11. So this vector ought to be 3 units here, 11 units here. Now this is a very simple picture. It's simple to do, but if you're not familiar with it, then it's probably going to look unfamiliar, isn't it? This is what a whole lot of linear algebra is talking about. Vectors being represented by matrices and column vectors and being transformed in a way we'll see. I've actually got some introductory videos from other courses that I will probably ask you to look at. If we have vectors with columns of length 3, then we're talking about 3-dimensional space. So we could have vectors in 3-dimensional space. If we've got vectors of length 3, then we represent that by a space with x1, x2, x3 here. And we can add those vectors, we can manipulate them. Everything we can do in 2 dimensions, we can do in 3. And of course, we're not confined to 3 dimensions. We can go to 4 dimensions or 5 dimensions or 738 dimensions or 5 million dimensions. And we can't visualize 5 million dimensions, can't visualize 4 dimensions. But by understanding and having an intuition about what happens in 2 or 3 dimensions, we can sort of visualize what's going on in those higher dimensions. At least we can get an intuition about what's going on in those higher dimensions. So if you aren't familiar with vectors in the first place, I have to assume you're not that familiar with planes and 3-dimensional space and stuff. We've already talked about it, where an equation can represent a plane. Talked about that last time and how planes can intersect. So we're beginning to do that. So I'm going to kind of ponder where you're at so we can kind of fill in a few details. Unfortunately, pre-calculus courses, especially second semester pre-calculus courses, if you haven't taken them here, are often come up short. That's all there is to it. And they come up short in the trigonometry. It's essential for understanding these things. Now, the right angle trigonometry, they always do quite well. If you had a trigonometry course, you're good. But we're going to have to fill in a few gaps here, so we'll work on that. In the meantime, you'll have an assignment. You have section 1, 2 that's due on Sunday. And again, I don't assign it on Sunday with the idea that you're going to spend Sunday working on it. You can work on it Saturday, you can work on it Friday. And then section 2.1 will be due on Tuesday. And then there'll be another section due on Thursday, and I'll do what I can to prepare you with a video for to replace Tuesday's class so we can stay on track. And the section you have due, the first 2 sections of chapter 2 are not too bad, but they're really important for understanding what goes on later. Then you're going to get into some sections that are a little more challenging. So stay on top of it. If you, one thing I notice is that there's a tendency in this course, almost everybody, to do the homework, not exactly at the last minute, When I got up this morning, about 7 o'clock, I checked and everybody had done it. When I checked last night, about 9 o'clock, I don't think only one person had done it. And so, you know, and nobody had started on it at noon yesterday. Best to start the homework as soon after class as possible when the things you've seen in class are still fresh in your mind. And if you don't do that, at least spend 10 minutes. Take some notes, review it, look at the videos, and review those. It turns out that Zoom is doing a pretty good job of getting these videos done quickly. So I should be able to email the video out, by hopefully early afternoon, and just flip through the video for 10 minutes as soon as possible after class, because whether you totally understand what you're saying or not, get your brain working. Now, if you think you understood everything and think you're still going to understand it, Sunday at 10 o'clock when you start the assignment, and hopefully can get it done in 2 hours, fine. But I really do strongly recommend refreshing yourself. Okay. There's a little bit of writing that I'm going to ask you to do also, mostly just an introduction, and then just a little bit of mathematics. Something shouldn't take you 30 minutes, maybe not even 15. So kind of expect that. I'll give you an email on that. I just want to check and make sure that we're able to get things, handwritten stuff through email and so forth. And then just, look at a little bit of your mathematics work, just something simple. Okay, any questions? Well, if not, you're welcome to go. And we'll pick it up next time. Thank you. Donovan?